We're group number 4, and our goal in this lesson is to explain the learning target, which is to evaluate limits analytically with focus on direct substitution and special trig limits. You can use direct substitution in a well-behaved function. Well-behaved functions are functions that are in the simplest form or it's not in an indeterminate form. For example, the limit as x approaches 2, x over 3 plus x. You can directly substitute 2 in because you won't get the indeterminate form, which is 0 over 0. On the other end, if you were to use a not well-behaved function, it would result in you getting indeterminate form when you directly substitute. For example, limit as x approaches 2, x squared plus 2x minus 8 over x squared minus x minus 2. If you simply directly substitute it at this point, you get 2 squared plus 2 times 2 minus 8 over 2 squared minus 2 minus 2, which gets you to 0 over 0, which is indeterminate form. However, it is possible to solve a not well-behaved function, but you'd have to simplify it first. For example, limit as x approaches 4, x squared minus 16 over x minus 4. If you were to simply directly substitute at this point, you get 4 squared minus 16 over 4 minus 4, which would lead it into indeterminate form. But if you were to simplify it down to the limit as x approaches 4 as x minus 4 multiplied by x plus 4 over x minus 4, you could cross out the x minus 4 on the numerator and denominator, which would leave you with x plus 4 over 1. And if you were to directly substitute at that point, you'd get 4 plus 4, which equals 8. So the limit of x approaching 4 of the function is 8. So you might ask, why is it important to have the limit notation at the beginning of your function? Limit notation, meaning limit as x approaches c, is necessary when solving or simplifying a limit. It's necessary because without the limit notation, it doesn't contain the undefined point in graph. The graph on the left is different from the graph on the right. The graph on the left shows the limit as x is approaching 2 for the value of x squared. Normally, 2 would work in this function and it would equal 4, but because of the limit notation being there, it would cause there to be a hole at 2, 4. So x approaching from the left and x approaching from the right will give you the y value of 4. On the example on the right, however, it doesn't have the limit notation, which means 2, 4 would exist. Limit notation is necessary when you're doing a limit function. In this example, the limit as x is approaching 3, x squared minus 16 over x minus 4. You need to keep the limit notation in the simplification process. This is so the function remains a limit function rather than a quadratic or a linear. You no longer need to use the limit notation when you're directly substituting your x value into the equation. However, when you write it out finally, it must remain in limit format. However, you do not need to write out the whole function. You can simply use f of x. There are two special trigonomic functions that will always end in the same limit. They are limit as x is approaching 0, sine of x over x. The limit for that is 1. The other is limit as x is approaching 0, 1 minus cosine x over x equals 0. The next trigonomic function is limit as x is approaching 0, 1 minus cosine x over x equaling 0. In this example, limit as x is approaching 0 is 2x minus 2 cosine x squared over 2x squared. When you are simplifying this, you can factor out 2x from both the numerator and the denominator. Since you have 2x in the numerator and denominator, they cancel out, which leaves you with the base trigonomic function, which is limit as x is approaching 0, 1 minus cosine x over x equaling 0. So let's end this lesson with a review. In this case, we are going to show you indeterminate form and then how to simplify it to find the limit of this function. This function is limit as x is approaching 3, x squared plus 3x minus 18 over x minus 3. If you were to directly substitute at this point, you would get 0 over 0, because 3 squared equals 9, plus 3 times 3, which equals 9, minus 18 equals 0, and 3 minus 3 equals 0. However, if you were to simplify the problem first, you would end up with your limit. X minus 3 is both on the numerator and denominator, so they cancel out, which leaves you with limit as x is approaching 3, x plus 6 over 1. Directly substituting 3 in for x, you get 3 plus 6, which equals 9. So the limit of the function as x is approaching 3 is 9. So let's say you have two special trigonomic functions in your problem. In this case, we have limit as x is approaching 0, sine x multiplied by 1 minus cosine x over x squared. What do you do then? Well, you can separate the two functions out into their base problems so you know their limits, which is sine x over x multiplied by 1 minus cosine x over x. Because in multiplication you just multiply the top by the bottom, this would result in the same equation that is above. So, you know that sine of x over x gives you the limit value of 1. And 1 minus cosine x over x gives you the limit value of 0. You just multiply these two together to find your limit. So the limit as x is approaching 0 for sine of x multiplied by 1 minus cosine x over x squared is 0. Bibliography. Some examples are from www.niu.edu. Some examples are from the calculus book by Larson, and the rest are from Creative Innovation.